Okay, good afternoon. So I'm happy to make a presentation about some of the AI system and application technology that we are working on right now. So this is going to be like a pretty fast-paced presentation. So I'm trying to do it sort of like mostly in terms of demo, so that we can show you what we are capable of doing. So the first thing is that last year, I gave a presentation in the same forum about some of this high-performance DNN training system that we are building now. And this year, we indeed are able to deliver one prototype for you. So it's in the back, and later on there will be a separate presentation on this. But I'm going to go over some of the general picture about why we are doing this. We call this a private DNN training system as opposed to public. Public are things done by Amazon, Google, or Microsoft. So we all know what AI is, right? Everybody is talking about AI. Nowadays, when we talk about AI, we mainly talk about deep neural network. And to me, DNN gave us the following possibility. Previously, we write program, right? We define spec, we devise algorithms, and we write code, and then we get our software. In the future, we label data, and we invoke this DNN training machine, and then we can create DNN model. And DNN model looks like that, right? And then in order to do this, we need a good DNN training system to create DNN model, right? And that's what we are talking about here. And we believe that DNN training will be a very important workload in future data centers. Like previously, a lot of programmers writing programs. Now you don't need to because you have DNN training. They are going to produce software for you. And this software will be in the form of DNN model. That's the difference. Now, to do DNN training, you can do public DNN training, like Amazon, Microsoft, Google. These big guys, they are doing that. Or you can buy your own DNN training appliance and do it at home. That's what we mean by private DNN training appliance. And the most famous one of this private DNN training system is, of course, NVIDIA's DTX. So if we do an anatomy of a DNN system, what does it look like, the DNN training system? Of course, you need to have an x86 server of some kind, right? First, you have that. And then you plug it in a bunch of GPU. You can use NVIDIA GPU, AMD GPU, even in the future, Intel GPU. Or if you want, like in the case of Microsoft, they use FPGA. So you plug in some of these accelerators into x86 server. And then you need to have an operating system of some kind. They preferably support some kind of container, right? And then on top of that, you need some sort of compiler. Remember the DNN model that I showed you in the last slide? You need to compile that DNN model into some executable code in order to run on this kind of hardware. And then on top of that, you have this DNN training framework, the thing that we are familiar with, like TensorFlow, Caffe, or nowadays PyTorch. These are all famous DNN training frameworks, allow you to train things and then get your DNN model. But then you need to run this DNN model on this hardware. And then finally, you need some kind of what we call integrated development environment, like to help you to reduce the amount of DNN training time that you need. And a complete DNN training system or appliance should consist of all of them, right? And then that's what we are trying to do. So we have a program called Open AI Training System Program. This is what we try to build. We think that this is a new category of system, private DNN training system, that may form an industry on its own, right? It's a market that we can try to shoot for it. But we are shooting for open. Unlike NVIDIA, it's very proprietary. It's a sort of NVIDIA's own design, and everything is owned by NVIDIA. So we are hoping that the accelerator doesn't have to be NVIDIA. It doesn't have to be a server-grade NVIDIA's GPU, like this P100 and T100. It's server-grade. You can use gaming GPU if you want. You use AMD, you can use AMD's gaming GPU, or you use Intel's upcoming GPU, and so on. So we want to support all this hardware. So that's one thing. That's why it's open, right? It's open. And then in terms of the software interface, we support CUDA or OpenCL. And in terms of framework, we support all the general sort of DNN training frameworks that are currently in use. And then, of course, in terms of system architecture, we are hoping that the number of GPU could be slightly higher, like more than 60, for example. And in particular, in order to have a good training performance, you need a high bandwidth inter-GPU communication. Now, in the case of NVIDIA, they use something called NVLink or NVSwitch to do that. But that's a proprietary technology. We want something more open. So we are hoping that we can use PCIe technology to provide a higher inter-GPU communication. Right? So that's the game plan of what we are trying to do. And then to do that in Taiwan, a couple of months ago, we started this Taiwan AI System Alliance, where we couple this server manufacturer or industrial computer hardware manufacturers or software stack developers and even users together to form such appliance to develop this this open AI system sort of program. And these are the current members of this particular alliance. And we also, as I promised last year, that in 1 year we are going to deliver a sort of a prototype that's pretty close to product grade. And this is what we have. We call it E3 DNN training system. Now, the first thing you see is price. So this is the list price. Of course, we don't know the cost of NVIDIA, but this is the list price. And this is more or less our list price. Okay? And so this is price-wise. It's going to be cheaper, of course, because we use the cheaper components. But then if you compare not just price, but in terms of per dollar, per US dollar, how many training image you can process. And if we are one, then DGX is about 0.37, right? So it's more cost effective, right? Per dollar, how many images per second you can do, then we are about 3 times as big. This is with respect to a particular workload. For another workload, we are about 6 times better, right? So that's another picture. And like I say, this is because we are using cheaper GPU to do that. And it's true in terms of absolute performance, this particular prototype is not as great as DGX. But in terms of per dollar, what kind of performance you can get, it's like 3 times to 6 times better. So that's like a significant difference. That's one, based on this price point. So that's the first thing I want to give you an update. Last year I say something, this year I deliver. So that's the basic message. The other project we want to talk about is some sort of robot. We call it companion robot for geriatrics. Geriatrics for those means old people. This means old people. That's the word for old people. Right? So why do we do this? Like, there's a societal trend. I think in Taiwan as well as in Japan. So we have increasing number of older people living alone. We call it open life. Okay? Because of what? Because of longer life expectancy and urbanization. Right? All the young kids go to the cities, right, and leave their parents at home, and so on. And we all know that this is a societal problem. Healthy aging is very, very important. Right? If you have like a disabled parent, it will create a lot of burden to the family. Right? So we want to create something so that like when the parents become something like 70 years and older, then we start to say what kind of things we can do for them. Right? That's the motivation. And like this is another sort of very alarming statistic. Like in US, they are in 2017 there are about 5.5 million dementia patients, and the total cost, the care cost, is about $260 billion for them. Right? So that obviously is a very important sort of burden. And to do that, what we want to do, we want to promote the active social engagement, right? And possibly early diagnosis and treatment. But in particular, we want these older people living alone to have active social life. That's the key thing. Like, that's what we want to do. Right? And why is that? It turns out that medically, loneliness is not a psychological condition. It's a disease. This is a medical fact. That if you are lonely, you tend to die. That die early. Right? That's basically a medical. So we want this active social engagement. Build some robots that can encourage active social engagement. That's what we want to do. So ideally, we want to involve friends and family. Right? It's not just for you yourself. You have to learn to socialize with others and so on. All your friends and family members have to help you. That's really what we want to do. And in particular, when we build this companion robot, who do we want to sell this robot to? Not to these old people. We want to sell them to the children of these old people. So what we want to address is the pain points of the children of the old people, not old people, right? And what are the pain points of these children? They want to, but they cannot keep close tabs on what they are doing. You know, everybody is busy making a living. They don't really have time to keep track of what their parents are doing. And second is that even if they want to engage with their parents, I mean, at least in older people involved in this project, like sometimes they call their parents, the conversation cannot last longer than 1 minute because I have nothing else to say to them. I don't know what to talk to them about. Just don't have some common thing they can talk about. So that's another thing. And then of course, peace of mind. I just want to know that there's somebody take care of the parents for me. I want that peace of mind so that I can focus on my career, my stuff, and so on. These are the pain points for the children of all people, right? Not all people, once again. So we are trying to address their pain points. So then we say that let's come up with some spec for this. Then the design principle is that you cannot ask these old people to wear any kind of sensor. This is doomed to be failure. You cannot ask them to wear any sensor. That's number one. Second, you have to respect their privacy. What that means that you cannot take camera into their bedroom. No camera into the bedroom. That's the number two criteria. So in the end, such a companion robot to all people living alone, they can be just one-on-one, almost like our pet, like our iPad-like thing, like electronic photo album, personal video communicator, and entertainment and gaming. So these are pretty easy, nothing special. Whatever you can do with the iPad, you can do it here. Right? More importantly is to friends and family. This is the second class of user of this robot. So they can provide safety, emergency alert for when they fall, or when there's a heart attack, or when there's some household emergency, fire, gas leak, and so on. Or you can report on living quality. This is our main focus. How does this particular person, the living quality of these old people, how do they live? Do they sleep well? Do they eat well? Do they feel good? Do they have enough exercise? That's what we want to do. That's what we want to capture. And it allows the children to teleoperate this robot. It's not just meant to be used by the old people themselves, but their children, right? So they can teleoperate. And they can provide the concrete material to allow these children to show concern. That's very important. I have nothing else to talk to my parents about. Now I give you something that you can talk to your parents about. And give you the right time to prompt you that this is the time to call your parents to talk about this. That's what we can do for you, right? So that's what this robot is. And we call this amiibo. So it looks something like this, right? And then of course you can do two-way video and photo sharing, so this is all easy. More importantly is this. We can say things like, does the person have enough exercise and eat well, and does he socialize with others, phone call or chat? Or does he feel good, and does he sleep well? So that's the main thing we want to capture. Some robot at your parents' house, he can tell you all this information about this particular person. So that's what. So in the following thing, I'm going to talk about some of this technology. The first thing is, of course, facial recognition. So these are all pretty standard. I'm going to skip this. I just want to show this to you. So here there are two approaches to do facial recognition. On the left is a traditional AI approach. You extract certain feature, and you based on that feature, you do classification. On the right is purely AI. You just take the image and then label them, and then I do it. Now you can see that sometimes you can see that even with mask, we can carry that. This is very important in a hospital environment. A lot of people are wearing masks, so I should be able to do that. And you can see that here, I can detect that, but this one cannot, because no, this is AI, this is not AI. So it's actually more powerful and more sort of effective. So this approach can deal with things like you can wear masks or glasses or even faces as a large angle. Like in this case, large angle, you can detect it, but you cannot. So that's the difference between the AI approach and the more traditional DNN approach and more traditional AI approach to face recognition. Okay, so in the next, I'm going to show a real-time demo for that. So let's go. So we can switch. So here another thing is that it doesn't require a long training time. So beforehand, when people walk into this room, we already capture them, and now we can try to recognize some of them. All right, so let's go. 就去了，没关系，就做了嘛，没关系，无所谓，看一下照谁都可以。So presumably that's one person. Okay. So the more important thing is it doesn't take like weeks or hours of training. Like in real time, people can register their image, and then from this point on, we can see them, right? So that's the idea. And I have to be. Okay, so this is sort of somewhat unusual, but I have to admit that some of the commercial grade face recognition engine can already do something like that. It's almost like a basic thing. Like, when you have a new customer, you want to capture his image in the future, you can recognize them without too much retraining. Okay, so we can switch to the main presentation. Okay, so then this is just a performance number, so I'll leave it for your reference. Right? We try different kind of words then. Once I can recognize this person, now I want to know, is this person in which mood? Happy, sad, and so on. That's what we want to do. So can we play the video? Just play the video. So we can recognize this person, we can also recognize its mood. And so this is in real time, we can track this many faces, and for each face, we can track its mood. Now the accuracy is around 80%, right, at this point, right? So for us, in this particular application, we mainly are interested in sad. Because we want to know when our parents are sad. That's kind of important. Happy, of course, we want to know. But when they are sad, we definitely want to know. And so that's important to us. Okay. So that's a facial expression. And then we want to know whether they eat well. That's important. So again, this is camera-based. So suppose you have a dinner, and then this robot will come along and try to scan the food, and try to know, right now we can say, where is the food? So the food container, and what kind of food. Here we can tell you the type of food, like rice, pork, fish, vegetable, and soup. And we also can check portion change. Like maybe the parents is not in a good mood. She doesn't eat too much, and we want to know. Or that maybe all parents tend to be sort of economical. They don't want to spend too much money, so they tend to use leftover food. Whatever they had last meal, they use it again this meal. We also want to know. Like leftover food, we also can detect that. So that's dial analysis. Right? Again, you don't have to do anything. We just use camera, and the robot will come along and then look around and see what happens. And then, in terms of activity, we do fall detection. There are a lot of people already can do fall detection, but here our fall detection use both audio and video. So let's just see the demo. For this case, it's a video. So once this shows how many seconds. You see when the person fails, you can call up the daughter or whatever children. Say something is wrong. Okay. And now you can zoom in to take a closer look at it. So for the daughter to take a look at it. And she's saying that, how are you? How are you doing? And he's saying that he needs an ambulance. Right? So that's one. In the other case, the camera doesn't see it. So the person just to make a sound, and then you can detect it again. So in both cases, either video-based or audio-based, we can detect it. She says that it's on the right side of Amiibo, this particular robot. And then now it's the daughter that's controlling this robot to take a look at the parent, whether how is she doing. All right. So, okay. All right. So that's fall detection. And then finally, we want to know whether they sleep well. And remember, I say that no camera inside the bed, inside the bedroom, and inside the living, your sleep places, right? So here we use a technology called Wi-Fi as a sleep quality sensor. So since you cannot use camera to sense anything, and we don't want them to wear any sensors, so the only thing we have is to use Wi-Fi. And how does it work? It looks something like this. This is a bed, and this person lie here. And the person just has to put his smartphone beside him, probably like within 1 meter, right? And turn on the Wi-Fi. And we can use a traditional AP to sense this person's breathing rate. We can detect it, right? So nothing else. Go to bed, put your smartphone on the side, turn on the Wi-Fi. That's it. I can see your sleep quality. So So we'll show the demo here. Okay, so remove it. So here, this person uses this particular position called soldier, and it's breathing at the rate of 10 ppm. And this is 10-10 here. Here, this is each approach. This is a traditional approach, so it's more accurate, basically. And the first one is the ground truth. This is a little bit fast, right? And there's another position, face down. Ground truth, E3, and somebody else's approach. Right? So it's 15-15. Right? And finally, another position called fetal position, like this. Again, 15, and then E3, and then other approach. Right? So this doesn't require any sensor. There's no camera. And just put your smartphone beside, you can detect your breathing rate. So that's the robot I'm talking about. Mainly we can say is a person sleep well, eat well, in good mood, whether there are any safety emergency, and then other things, right? So that's what this robot can do. That's the focus. Like, we don't focus too much about whether the robot can interact with the person verbally or not. That's not really our focus. We just want somebody who can take care of the person, the old parent living alone. That's really what we want to do. The other project that's related is also using a lot of AI technology. We build this AI technology to provide ambient intelligence for next generation retail store. So what does it mean? Like traditionally, we all know that these retail stores are closing shop. Just recently, Sears in the United States are filing for bankruptcy protection. Physical retail stores are in bad shape. They don't really know where else to go because they are beaten down by Amazon like crazy, right? So we are saying that what kind of ICT technology can help them to do things. And then we interview a bunch of people, and then they decide to say that nowadays, the objective of designing a physical retail store is to optimize the shoppers' try-on experiences. Like, if you want to try on some food, some clothes, some shoes, something, you have to optimize that trial experience, make them happy, so that they will go to this physical store. And you want to capture the shopper and merchandise interaction. The reason that we set up a physical retail store, so that shopper can come in and try stuff, and we want to capture everything that happens when the shopper try on some merchandise. That interaction we want to capture, right? So in the end, what we want to do is to capture whatever can be captured in an e-commerce store, in a physical store. When you are doing your e-commerce browsing, you browse this page, how much time you spend on that particular page. So we know exactly what kind of things that you are interested in. If you are browsing a particular e-commerce site, we want to achieve the same level of visibility in a physical retail store. Exactly the same. Like when you go to a store, like we get to know how many shoppers are in my store. So that's easy. Just do people counting. Then for each of the shopper, what's the trajectory of this shopper through my store? I go to that particular section, and then that's A section, and then B section, and J section, and so on. I want to know that trajectory. And we want to know what merchandise that this shopper interact with, this particular jacket, the particular clothes, and so on. Pick it up, take a look at it, and we want to know. And we want to know that the person like that thing or not. Right? So that's what we want to do. So in the end, we want to provide the ICT technology so that the physical store owner get to have this kind of information. So that's what this technology is. So the flow is very simple. Like you have to follow this thing. So I'm not going to go into the detail, but eventually that's what is happening there. So the next, there will be a bunch of technology that we need to develop in order to achieve that vision, right? The first thing is person re-identification. So a person comes into the store, and the person is walking around the store, going through multiple antenna, multiple camera, and we want to know this is the same person, right? The person goes through a store and captured by multiple camera, and we want to know it's the same person. That problem is called person re-identification. We don't know who this guy is. We just know it's the same guy, right? Even it appears in different cameras. So that we can solve right now. Then we can also use that Wi-Fi technology, not just for breathing rate detection, but also for location, right? And again, the same technology applies. So I'm going to skip that theory. So here it just shows that as a person walking around the store, this is a top-down view. You can see that this guy is on which location within the store, and so on. And this particular technology, Wi-Fi based position technology, right now we can do something along the line of about 70 to 80 centimeters. That's the resolution we can do right now. Again, we are relying on the person carry some smartphone, and that smartphone turn on Wi-Fi. That's all we are relying on. Okay. And the next step, now I know a person that comes in and then walking around, and I know that person's trajectory. The next thing is I want to capture shopper and merchandise interaction. Does the guy pick up something, all right, and take a look at it or not? So we are able to have this different classes of action, like empty-handed, occlusion, hold basket, hold car, and so on. A couple of these action types, the interaction type that we can capture. But before we do that, we have to do what's known as skeleton detection. Okay, so it's easier to explain this just by. Yeah. Okay. So skeleton means that for each individual, we can come up with a skeleton. We can detect a skeleton. It's a movement, a body movement. And then the next step is that we have to say this body movement can further deduce the interaction between this person's body movement and the merchandise, the actual stuff in the store. Right? So we can then deduce that does this person come into my store at the time T1, it's picking up a jacket. I know this thing. Right? And then we can aggregate all this information. So imagine that this guy is walking around in some mall, and in each of the store we can get this kind of information, and we can aggregate that. Then I know this person's physical trajectory in the mall and the interaction history throughout the entire trajectory and the shopping experiences. Okay, so finally we want to check out, right? So once you have this, we can check out. And then here we do automatic checkout using camera again, like on some conveyors chain. And all you have to do is just put this thing on top of them, and we use camera to register, to recognize them. And we also can detect some kind of anomalous behavior detection. Like you don't actually, when you have some object that you are supposed to check out, but you don't, you can also recognize that. So this is used in a convenience store. So right now we can do like, out of 1,000 merchandise, you can pick any 3 items and then put it on that. And then 97% accuracy within 1 second, we can finish the checkout process. Okay, and this is showing the demo. So just put 1, 2, 3 there. And this is the older version, it takes slightly longer. Once whatever you recognize, we use a projector and project here. So we are waiting for 1, and then we are done. And go. So this takes about 4-point-something seconds, and now we can finish the whole process in 1 second. So that's the automated checkout. And this is going to be in field deployment sometime in the coming November in one of the convenience stores in Taiwan. And then we have this something called, from this unmanned convenience store to this what we call unmanned open vending machine. Now we all know what vending machine is. This is very popular in Japan. So it's closed, right? It's like everything is inside, and you put in money and you do it. And we say it's open because there's nothing to block it, right? And it's unmanned. So we are trying to put in some camera so that we can detect whether things get picked up and by whom and so on. So this is particularly useful in an office environment. Like people don't want to walk too far away, and then we can do something like this. And used in this technology, like you can recognize the individual, recognize the things that get picked up, and then eventually restart it. So again, let's see a demo to do this. So this is pretty short, about 30 seconds. So the process is that you step on some mat, on that. So and then you got IDU, and then you pick up food, and then so on. This is in one case. So there's no need to scan. We know what you pick wake up, and this is trying to show it's very fast. Like, if you are really hungry, like within 2 to 3 seconds, you can pick up your food and eat. And this is show how the step can be stacked. Like, you need people to restock the things into this intelligent chef. So if you put your food in a different, wrong spot, this thing will not show up. Like, in this case, like, putting the wrong spot is for you to remind you. Again, wrong and right, and then everything done. Okay, so that's the flow. So it's not like a complete unmanned convenience store. It's meant to be used in an office environment where you can have. And this is apparently this is very popular in China. Like, there's a big boom about this kind of thing, but it doesn't really come with all the intelligence that we have here. It's mainly rely on people to scan food and so on. So when you do a lot of problem, it has a lot of loss and so on. But with this more intelligence technology, you can address this problem. Finally, I just want to mention this technology. Right? This is we think is a very, very important technology. We call it super resolution. This is actually a standard term. Here that you have an image like this, the quality is not that great. Going through some sort of AI or CNN network in the middle, I can enhance it to something like this. Right? That's what we can do. But it can actually be used for all kinds of things, right? So it is essentially what it does is if you give me a high quality image and low quality image of some sort, and if you give me such a pair, 1 million such pair, then I can create such a model for you. Right? And then you can do this super resolution for you. And so it's an image to image transformation. And the application is something like this, like we apply it to license plate recognition for roadside camera. Right? In the police department work, they need something like this. Like traditionally, you have this not so great license plate image, and after going through super resolution, that's what you get. Right? And what's the implication of this? First of all, we can use this kind of technology to deal with the license plate of a motorcycle, not the typical automobile motorcycle. So the license plate tends to be small. Previously, we don't have a good way to deal with it. With super resolution, now we can. That's one. The other thing is that in one of the test sites, it used to have pretty low quality camera, like this kind of camera, not that great. So the images that are produced by these cameras are essentially useless for license plate recognition. But with the super resolution, now this kind of not so great camera suddenly become high quality camera, because now we can enhance their images. So that's also a very good application of super resolution. Finally, we also apply this technology to a biological cell recognition project. So it turns out that for some biological cell, you can have an optical photo. You can take a picture using optical camera. Or you can use another way called fluoresce way to detecting the patterns in the biological sort of cell. Now, if you give me such pair, optical photo and fluoresce photo, such a pair, you give me 1 million such pair, then I can train them. So in the future, you don't have to do this anymore. If you give me an optical photo, I can produce the corresponding fluoresce image for you without doing anything to capture that image. It turns out that with this process, we can achieve about 98% accuracy for doing that. So from this point on, all you have to do is just take optical photo, and then we can produce the other kind of photos for you automatically with a reasonably high accuracy. And that's another application of super resolution. Okay, so that's all I have. So thank you very much.
Thank you very much, Dr. Chiueh. For in Japanese, ドクターチェが今話をしたことをですね、OCPGA の運営委員の、福原さんにサマリーをしてもらいたいと思います。よろしくお願いします。
こんにちは、福原です。今日はですね、チェさんとってもたくさんお話ししていただいたので、簡単にサマリーしづらいのですが、スライドを見ながらサクサクっと、簡単なコメントだけしていこうと思います。最初はですね、去年のこの場でも、発表していただいたんですけども、ディープラーニングですね、ディープラーニングのアプライアンスをイトリで準備しました。で、非常にコスト、パフォーマンスが良い アプライアンスを準備して、このような団体も立ち上げたそうです。で、ここですね、とても、コストエフェクティブですよというお話でした。で、こちらも去年はコンセプトだったんですけど、今年はもうデモが、提供できるという状態になっていますというのが、先ほどのお話でした。で、この前振りの次がですね、ここも大事なところで、ロボットですね。何が大事かというと、やっぱり台湾でも、老人の1人で暮らしている老人、っていうのが問題が出てきているようです。で、その老人に対して、どうやってケアをしていくか。で、この彼の、なんて言うんでしょうね、ビジネスモデル的なポイントがいいところなんですけども、老人を心配するのは子供です。子供はその自分の親を、ちゃんと見守る義務を持っているので、このロボットを買うのは子供です。老人に、それ以上の、負担は強いません。子供が、ロボットを買って、自分の親の面倒を見るというモデルができるでしょうということですね。で、左側がご老人の方に対して何がいいですか、右側は、その子供さん、ファミリーの方、家族の方に何がいいんでしょうかというので、現場では寂しくないところですね。子供の方はちゃんと、遠くに離れた親御さんの状態が分かるよみたいなコミュニケーションできますねということになると思います。で、こんなロボット、後ろにいるのも多分これのコンセプトと同じと思いますけども、ロボットが今、作ってみましたということと思います。で、次はちょっとここからまた変わって、ここからは、顔認識ですね。顔認識の、ソフトウェアというか、そちらがディープラーニングでうまく動いてます。なので、ここにいる皆さんの、顔も撮ってデモをしたと思います。で、動きながらのビデオでもできますよということですね。で、ここは感情も、読み取れます。個人の認識だけではなくて、感情までも読み取れますという話でした。で、人だけではなくて食べ物も、こんな感じで読み取れてますねということですね。で、次はこれはビデオだけじゃなくてオーディオでも、同じようなものが、できて、ここでもありましたけど、人が倒れた時に、ちゃんとそれをケアするというようなこともできそうです。で、次がまたこれ話はテクノロジー変わるんですけど、今度はですね、Wi-Fi を呼吸のセンサーに使いましょうというなんか面白い、私も初めて聞いたんですけども、ものです。つまりはですね、これを見ると分かるんですけど、Wi-Fi のこの電波強度ですね、電波強度が人の動きに影響されて変わります。それを、解析して、呼吸が1分間に何回しているかというようなものまで解析ができますというテクノロジーです。で、これで、先ほどこのデモでは、何個かありましたね。1分間に10回だとか15回とか、どんな体勢で寝てるみたいなのが、センサリングできますというテクノロジーの紹介でした。で、次がですね、ここから最後ですね、今度は小売店の話です。小売店の話で、最初の子は、どういうふうに人が動きますかというのは、現状を分析するような、どちらかというとマーケティングに使えますというお話と、この辺もそうですね、人の動きがどうですかというようなのを、ここも Wi-Fi を使って場所を特定したり、ビデオを使って、場所を特定したりというのの組み合わせで、人の動線が、解析できるということだと思います。で、もう一緒ですね、同じような、ビデオを使った解析の例です。で、ここでまた小売なんですけど、またテクノロジーが変わって、ここは、会計ですね、会計システムの、デモお話でした。ビデオでパッと読み取って、その商品を読み取って会計ができるというようなものですね。非常に早く1秒で読み取れますというお話があって、これは面白いと思います。今まで左側のような大きな自動販売機が必要だったんですけども、それがこのカメラだけで、会計システムができてしまうと。もちろんビデオデモにあったように本人を特定するっていうのが必要なので、オフィスの中だったらできるっていうような制限はあると思うんですけども、こういった簡単にちっちゃく安く自動販売機が作れますというデモだと思います。これですね、ここで、デモのビデオ出たと思います。で、さらに次はまた別の、テクノロジーで、これはスーパーレゾリューション、 これはもう面白いですね。カメラの画質がいいカメラを作ったではなくて、悪い画質のカメラで撮ったものをソフトウェアで解析して、高品質にしてしまうというソフトウェア技術のご紹介だそうです。テレビの SF 系のドラマでよくあると思うんですけど、見えないものがだんだんこうよく見えてくるみたいな、そんなのが現実になりつつあるんだなというふうに感じました。でこれはその一例なんですけども、車というよりはバイクですね。バイクのちっちゃいナンバープレートって読みづらいのが、これが、安いといいましょうか、質の良くないカメラで撮ったものでもちゃんと、ナンバーが読み取れるように分析することができますと。解析するようにソフトウェアで、そこをスーパーですね、スーパーレゾレーションにすることができますというような話だと思います。ここで最後ですね。でこちらはそれの応用で、そのソフトウェアの、画像の、トランスファーですねの、一つの例で、細胞を普通の光学の写真で撮ったものと、こちら蛍光ですね、蛍光の写真で撮ったものというようなものをちゃんと覚え込ませてやると、蛍光撮らなくても普通の光学写真を撮ったら蛍光の写真を作れちゃうというような、お話だったと思います。以上ですね。というようないろんなですねテクノロジーの話を、今日はたくさんお話ししてくれたので、私はお腹いっぱいなんですが、皆さん何かご質問はあるでしょうか。